Hey guys, so this was one of your homework questions. So here in this question, you have a system, and the system consists of a thin charged wire ring of radius capital R and a very long uniformly charged thread, which is oriented along the axis of the ring, right? So you have a charged ring, and you have a semi-infinite rod, which is oriented along the axis of the ring with one of its ends coinciding with the center of the ring. So one of its ends is present at the center of the ring. So notice this is a three-dimensional diagram. Your uniformly charged long thread is along the axis of the ring. Okay. The total charge of the ring is given as Q, and the charge per unit length of the thread is given as lambda. So in this question, we are supposed to calculate what will be the force acting between the ring and the thread, right? So uh, this is the question where we see one of the applications of knowing the concept of electric field, right? So we know we can calculate force between two point charges, but in other cases where we don't have point charges, this is one of the approaches we'll be trying to solve these kind of questions. And we'll say that the force acting between them can be described in two ways. We can say that the force acting between them is force on the ring due to the electric field of the rod, or we can also say that the force acting on the rod is due to the electric field of the ring. So both are valid approaches over here. We can solve the question by both the approaches, but I'll be making use of this approach. I'll be calculating the force of the ring, force on the ring due to the electric field of the rod, right? And we already know the formula for electric field due to a rod, and more precisely, electric field due to a semi-infinite rod. Electric field due to a semi-infinite rod is equal to, it has a k lambda by r component perpendicular to the rod, and it also has a k lambda by r component parallel to the rod, right? So you'll have both the components of field over here. So, and now this charge Q, which is the charge on the ring, is present in the electric field of this rod. So let me divide this ring into many small charge particles. Let me call those charge particles as dq, right? So let me concentrate on this dq first, that is the lower one. So there'll be a force acting on this dq due to the electric field of the rod. And what will be the electric field of the rod at this point? We'll have a component of electric field perpendicular to the rod, which will be in this direction. And that value is k lambda by r. We'll also have an electric field component parallel to the rod, and that will be in this direction, and that will be equal to k lambda by r, right? So this dq will experience a force due to the electric field. And let me write that as df. So your df will be equal to nothing but dq into e bar. That is the the small charge on the ring multiplied with the electric field of the rod at that point, right? So we'll notice that we'll have a force component. So I can just multiply dq over here. So this will be a force component perpendicular to the rod acting on the ring, and this is your force component parallel to the rod acting on this ring. Okay, and now if I consider a symmetrical element, that is the dq at the top, that is the dq we have at the top. Here also you'll have electric field due to the rod at this point, and the electric field of the rod once again will be, I'll have a radial component and I'll have a component parallel to the rod, which is k lambda by r this way. And even on this, we'll say that you have a dq present, and the force acting on this will be k lambda by r into dq in this direction, as well as k lambda by r into dq in the parallel direction, right? So if you notice from symmetry, you will see that these two components of forces will cancel out. So if I have to calculate the net force acting on that ring due to the electric field of the rod, I'll say it's summation of all dq into electric field component parallel to the rod only, because as we notice, your perpendicular components will cancel out even at these points as well, right? And all your parallel components will add up. All your parallel components will add up in this case. So then we only have to add up the parallel components. So this will become equal to integral dq into k lambda by r, right? K lambda by r, the parallel component of field is same at all points. So k lambda by r is a constant in this integration. So this becomes equal to nothing but k lambda by r into integral of dq. And integral of dq is nothing but the total charge on the ring. So this becomes equal to k lambda q by r, right? So the answer for this question will be option number D. So hopefully this question made sense. I'll see you guys in the next question.